Imagine a force of nature so powerful it reshapes coastlines. Now, imagine what happens when two of these monstrous systems literally crash into each other. Welcome to this explainer. Today, we're diving into one of the absolute most thrilling and, honestly, terrifying phenomena in meteorology, the Fujiwhara Effect. We're talking about gigantic swirling storm systems that cross paths and perform this complex, almost graceful dance in the atmosphere. It's dynamic, it's incredibly destructive, and the mechanics behind the whole shebang are just absolutely fascinating. Let's get into it. So, what actually happens when two gigantic tropical cyclones meet on the open ocean? I mean, it sounds like the plot of a ridiculous Hollywood disaster movie, right? We all know the kind of devastation a single hurricane or typhoon can unleash all on its own. But remember, the atmosphere is this vast, chaotic fluid. So every now and then, two of these absolute monsters find themselves sharing the exact same stretch of ocean. What happens then? Do they just bounce off each other like bumper cars? Do they cancel each other out? Well, the answer is way more complicated, and honestly a lot cooler than a simple head-on collision. Section 1. When hurricanes collide. To figure out what happens when they meet, you kind of have to picture the meteorological equivalent of a heavyweight title fight. The ultimate outcome of this clash is a process called cyclone cannibalism. Yeah, it's exactly as intense as it sounds. We aren't talking about two storms just gently brushing past each other and politely moving on. Oh no. When these massive tropical systems interact, they go to war. They fiercely compete for limited ocean heat, they fight for moisture, and they basically blast each other with immense vertical wind shear. In the most extreme cases, one storm literally devours the other. It absorbs all of its energy, all of its moisture, and mutates into an even more formidable beast of a system. Section 2. The science of the dance. Now, what makes this whole crazy interaction possible comes down to the underlying physics. We actually owe our understanding of this intricate dance to a Japanese meteorologist, Dr. Sakuhei Fujiwhara. Back in 1921, he figured out that these massive storms can literally lock together. Think about that for a second. 1921. That was decades before we had satellites orbiting in space to show us the big picture. But through pure observation and sheer genius, he discovered that when two cyclones approach each other, their wind fields and their vorticity fields, which is basically the spinning energy of the storms, interlock. They completely stop moving independently and they start dictating each other's paths. Today, over a century later, we honor that brilliant discovery by calling it the Fujiwhara Effect. The absolute key to this entire phenomenon boils down to a very specific number. The trap is set at exactly 1,400 kilometers. That is the critical distance threshold for tropical cyclones to begin this dangerous interaction. If two tropical cyclones wander within that range, which is, about 870 miles, the lock occurs. Boom, the physics take over. Now, as an aside, it's worth pointing out that for larger extratropical cyclones, which are physically way broader and more spread out, this interaction can actually kick off from up to 2,000 kilometers away. But either way, once they cross that invisible boundary, the dance is on. And of course, planetary geography sets the actual rules of engagement here. Because of the Earth's rotation and the Coriolis effect, these locked storms don't just, drift around randomly. Down in the southern hemisphere, they perform this stunning clockwise waltz around each other. Up in the northern hemisphere, same exact dance, just in a counterclockwise direction. It is this brilliant, terrifying display of planetary physics in real time, literally turning massive weather systems into temporary binary partners just orbiting each other out in the open ocean. So instead of just smashing head-on, these locked storms start rotating around a shared, completely invisible pivot point called the barycenter. Think of the barycenter as the center of mass. Picture two figure skaters holding hands and spinning on the ice, right? If both skaters weigh exactly the same, they spin around a point directly in the middle of their joined hands, perfectly balanced. Storms work the exact same way. If they're the same size, that pivot point is dead in the middle. But if one skater, or in our case, one storm, is massively larger and stronger, the smaller one just gets wildly whipped around them. Depending on the fight for ocean heat and the relative size of the storms, this atmospheric tango can result in one of four extreme outcomes. First, you've got mutual orbiting, where they just circle each other for a bit before eventually breaking apart. Second, we might see a dramatic track deflection. This is where one storm rockets off in a totally unexpected and usually dangerous direction. Third is ejection. This acts almost like a gravitational slingshot, where one storm gets violently flung away. And finally, outcome number 4, the complete merger. That's the terrifying cyclone cannibalism we mentioned earlier, where they combine into a single massive, highly organized superstorm. Section 3, the devastating loop of 2009. Okay, let's look at how this actually translates into a real-world nightmare. Back in October 2009, the Philippines faced a terrifying setup. Typhoon Parma was suddenly tracked by the absolute behemoth that was Super Typhoon Melor. Now, Typhoon Parma, known locally as Peping, was a remarkably strong, highly dangerous storm all on its own. But lurking right behind it was Super Typhoon Melor, or Quidan, rolling in as a Category 5 equivalent monster. Melor was undeniably the dominant force here. Because of the massive gap in their sheer power, the physics of the Fujiwhara effect basically guaranteed that Parma was about to get severely bullied by its larger neighbor. And bullied it was. Melor's massive atmospheric pull completely stalled Parma. Imagine a powerful storm starting to move away from land, only to be dragged backwards like it was caught in some sci-fi tractor beam. The very center was so heavily skewed toward the massive Melor that Parma literally stopped in its tracks. It looped around, made landfall again, stalled out, drifted back out to sea, and was then pulled back into land for a third time. This erratic, unpredictable looping subjected Luzon Island to nearly 3 continuous weeks of torrential rain. It was an absolute catastrophic humanitarian crisis. Section 4, Cyclone Cannibalism in 1995. For an even wilder example of an outright merger, we have to look back to the hyperactive 1995 Atlantic hurricane season. That season had a literal train of storms crossing the ocean, which is basically the perfect breeding ground for this phenomenon. Hurricane Iris was incredibly busy that year. First, engaged in a Fujiwhara dance with Hurricane Humberto, causing a sudden, sharp deflection in Iris's heading. But once Humberto moved away, Iris was not done. Tropical storm Karen wandered right into that 1,400-kilometer threshold, and a second, much deadlier dance kicked off. Now, because Iris was significantly larger, with a way wider wind field and a much more intense structure, the Berry Center was located almost entirely inside Iris's core. So, the much smaller Karen? Yeah, it didn't stand a chance of a balanced waltz. Instead of spinning gracefully around a middle point, Karen was forced into this high-speed, doomed orbit around Iris. The powerful outflow from Iris just started tearing at Karen's structure, pulling it closer and closer with every single frenzied rotation. The ultimate consequence? Karen was completely swallowed whole, which allowed Iris to re-intensify and accelerate northward. By September 3, 1995, Tropical Storm Karen simply ceased to exist as an independent entity. Its moisture, its spinning energy, its entire circulation, it was all completely assimilated into the larger structure of Hurricane Iris. Literally the textbook definition of cyclone cannibalism playing out in real time. Section 5. The Ultimate Forecasting Challenge. So why does all this matter for us? Because the Fujiwhara effect creates massive, massive unpredictability. These overlapping forces and erratic loops completely wreck our standard computer forecast models, which puts human lives directly at risk. Meteorologists rely on precise data to tell us where a storm is going and exactly when it'll get there. But when two wind fields overlap, translation speeds change drastically, just like we saw with Parma stalling over the Philippines. Standard models just can't accurately predict exactly when that lock will happen, or which of those 4 extreme outcomes is actually going to play out. Are they just going to deflect? Or is one going to loop completely backwards into a populated coastline? Which leaves us with a pretty chilling final thought to take away from this explainer. If the storms of tomorrow are fueled by warmer oceans, becoming bigger and significantly more numerous, well, the chances of these 1,400-kilometer encounters are only going to increase. How on earth are we going to predict this deadly dance? Understanding the Fujiwhara effect isn't just some fun meteorological trivia, it is absolutely crucial for our future safety. When the models fail and the storms lock together, human intuition and a deep understanding of these complex atmospheric mechanics are all we have left. Thank you so much for diving into this incredible topic with me.
Tropical cyclones are generally reliable machines. Driven by large-scale atmospheric currents, these massive storms usually track across the ocean in a steady, linear path. Looking at this standard weather map, we see how meteorologists use supercomputers to plot these predictable routes. By connecting data points, they can map a storm's trajectory and issue warnings to coastal cities days in advance. But occasionally, a storm defies the math. It might stop completely dead in the water, abruptly reverse its direction, or loop around to strike the exact same coastline multiple times. When a cyclone exhibits this kind of highly erratic behavior, the cause is rarely internal. It happens because the storm is no longer alone in the ocean. Despite our advanced satellite arrays, There is a hidden meteorological phenomenon that completely breaks standard forecasting models and injects pure chaos into the atmosphere. In 1921, Japanese meteorologist Dr. Sakuhei Fujiwhara identified the mechanics behind this anomaly. He discovered a rare physical interaction that occurs when two low-pressure systems drift into close proximity. For tropical cyclones, this phenomenon relies on a strict spatial boundary. The effect triggers only when two approaching storms cross an invisible threshold, sitting exactly 1,400 kilometers apart. The moment they breach that distance, the isolated systems begin competing for the surrounding ocean heat. Their outer wind bands tangle together, and their internal vorticity fields lock in place. Crossing that 1,400-kilometer line strips both storms of their individual steering currents. They are forced into a shared, highly volatile system that leaves standard tracking algorithms completely blind. The core mechanic of this interaction relies on a barycenter. The locked storms become tethered to a shared, invisible center of mass. In the northern hemisphere, they immediately begin a synchronized counterclockwise orbit around this central point. We can see this balanced orbit in action by looking at the 2009 interaction between Typhoon Parma and Super Typhoon Melor in the Pacific. Typhoon Parma was originally moving safely out to sea, but when the massive Super Typhoon Melor crossed the 1,000-kilometer mark, it grabbed Parma by its circulation and aggressively pulled it backward. This atmospheric tug-of-war caused Parma to stall out. Instead of maintaining its linear path, the storm was forced to execute a violent looping orbit. When two storms carry roughly equal mass, they engage in a mutual deflection. They pull each other off their expected routes, turning relatively safe trajectories into entirely unpredictable loops. That covers a balanced orbit. But what happens if the two storms locked in this dance are wildly disproportionate in size? On this 1995 infrared satellite map of a highly active Atlantic season, we can see the massive Hurricane Iris positioned right next to the much smaller tropical storm Karen. Because Iris was so large, the shared barycenter shifted dangerously close to its core, forcing the smaller Karen into a rapid, tightening orbit. On September 3rd, Iris completely swallowed Karen. Her circulation was assimilated into the larger storm, a process meteorologists call cyclone cannibalism. In a severely unequal matchup, the larger storm weaponizes the Fujiwhara effect to consume its rival. It absorbs the smaller storm's moisture and energy, allowing the victor to re-intensify and accelerate. Out over the open ocean, this orbital dance is a fascinating display of physics. But when these stalled, looping tracks collide with populated coastlines, the outcome is catastrophic. Caught in its Fujiwhara-induced loop, Typhoon Parma was forced to make landfall on the Philippine island of Luzon, reverse course, and strike the exact same island 3 separate times. This erratic, repeated path kept the cyclone parked over the region, resulting in nearly 3 unbroken weeks of relentless, record-breaking rainfall. The prolonged deluge triggered massive landslides, catastrophic flooding, and a severe humanitarian crisis. We can see the absolute destruction of coastal infrastructure here, entirely caused by a storm system that simply refused to leave. A Fujiwhara interaction weaponizes time. The primary threat shifts from maximum wind speed to the catastrophic duration of a storm trapped over vulnerable human geography. As our climate system produces increasingly active hurricane seasons, the probability of multiple storms occupying the same 1,400-kilometer patch of ocean steadily rises. This overlapping of wind fields strips meteorologists of their primary tracking variables, rendering precise landfall track predictions nearly impossible. No matter how powerful our forecast models become, or how thoroughly we map the oceans, nature retains the ultimate trump card. The Fujiwhara effect is a humbling mechanism. We can measure the atmosphere's physical limits, but we can never fully predict its chaotic engines.